Welcome, everyone. Today's explainer is all about the 360-degree mystery, where we're going to be unpacking the exterior angle sum theorem. You know, in math, we're always hunting for constants, those undeniable rules that kind of anchor the chaos, right? Well, today, we are zeroing in on one of the absolute most fundamental geometric rules out there. It's an elegant little concept that keeps our geometric universe perfectly balanced. Let's get right into it.
Okay, let's dive into this. 360. It's a magical mathematical destination. I mean, think about it. Numbers can often feel totally infinite, chaotic, and just wildly unpredictable. But 360, it is this perfect, highly satisfying constant that just keeps showing up time and time again to bring absolute order to our shapes.
So what exactly makes 360 an absolutely unbreakable rule in geometry? Well, to really grasp the unbending nature of this constant, we basically need to play detective. We have to look at the strict parameters that govern it, piece by piece, to uncover exactly why this number literally refuses to budge.
All right, peeling back the layers here, the very first crucial constraint is that our shape has to be a convex polygon. And this isn't just some casual suggestion, it's literally the foundation of the whole theorem. For this rule to actually hold up, every single interior angle has to point outward. Just one single caved-in corner messes up the entire mathematical rotation. So, for our operating framework, we are strictly locking in convex shapes, no exceptions.
Next up, we're stepping outside the shape itself. We're exclusively looking at exterior angles. Imagine you project a perfectly straight line extending right past any corner of your shape. The angle formed right there, between that straight trajectory and the next edge of the shape, that is our target metric. Those very specific angles, the ones sitting on the outside edge of our geometry, are exactly the components we're going to be adding together.
But there is a strict caveat here. You can only count a single angle per vertex. Sure, you could technically draw two intersecting exterior angles at any given corner if you just extended both lines, but the theorem strictly limits us to choosing just one per vertex to build our sum. So the crucial point is, we are just tracking a single continuous rotation right around the perimeter.
Okay, so the stage is officially set. We have three firm conditions required here. It has to be a convex polygon, it's n-sided, and we only count one angle at each vertex. Got it? Awesome. With these very specific constraints locked in, the underlying logic of the rule is about to fully reveal itself.
And this brings us to the ultimate truth, the exterior angle sum theorem. It states that the sum of the measures of the exterior angles of a convex, n-sided polygon is equal to 360 degrees. Boom. All those strict constraints we just broke down, they lead us right to this unyielding anchor. Honestly, it's amazing. No matter the shape, as long as it follows those rules, your total rotation is always going to amount to exactly one full circle.
But what exactly does n-sided mean for us? Well, the true beauty of this theorem lies right there in that little variable n. It means literally any number of sides. It represents totally boundless scalability. The shape can be super basic, or it could have 12, 87, or thousands of sides. That n means the theorem seamlessly scales to govern shapes that are as wildly complex as you can possibly conceptualize in your head.
And this brilliantly illustrates the whole concept. Just think about a simple three-sided polygon, a triangle, versus a massive 3,000-sided polygon. The triangle has three large, sweeping exterior angles. The 3,000-sided shape? It has 3,000 incredibly tiny little exterior shifts. But mathematically, they balance out perfectly. Why? Because walking the perimeter of any convex shape and turning at each corner means you ultimately complete one full rotation to face your exact starting direction. So the total rotational sum? It remains totally, absolutely fixed at 360 degrees.
Think about it like this. If you drew a convex polygon with a million sides, to your naked eye, it would honestly look like a perfect smooth circle. Yet the sum of its 1 million microscopic exterior angles remains exactly 360 degrees. Mind-blowing, right? It really begs a fascinating question to leave you with. If this unbending, absolute 360-degree rule so strictly dictates all of our flat two-dimensional planes, what kind of wild mathematical chaos awaits us when we start warping these shapes into the third dimension?